so that we know what's going on. So what we're going to do is we'll start with homework. We'll see how long it takes to deal with homework. And then, if we have time, we'll start the new thing. By the way, as an incentive, if we have time, we will be talking about the way that we used to calculate back in the olden days with slide rules and so forth. So I'll show you how this thing works, as well as, I don't know, other calculating methods, because they apply, there's applications to differential equations. Okay, so what sorts of issues did we have? Maybe we should restrict it to, let's start with the spring mass systems. Do those first. And I realize, I guess, does anyone else suffering with the metric book? Or just Luke? Luke's the only, he's got a special book. It came from like, I don't know, Australia or something. I don't know where it came from. Wherever they use metric, right? France, it's a French book. Wherever you got your book. Okay, so anyway, so maybe we could restrict ourselves to the normal version of the book, unless there's overlap. But anyway, did you have any trouble with the spring mass systems? It works out okay, or are there problems? I mean, mainly it's just setting things up properly, right? So that you have, let me just remind, just to make sure I know what I'm doing. You take the mass times the second derivative, and then the damping coefficient times the first derivative, and then the spring, the Hooke's law spring constant times the function itself. And that gives you and you set it equal to whatever your driving force is. And that's it, and then solve like you normally do. And we've solved these things so much that you can almost do it in your sleep, right? Yeah, excellent. Or you could do it while you're riding a bicycle. Yeah, Cooper.
The one where it gives us the f of t, we just plug that in for f of t.
Yeah.
And then we do the velocity and all that. We want to do that.
Oh, interesting. You have a choice. You can, so the ones that have the f of t, you can choose either to do it using that Wronskian, that would be the method of the variation of parameters, or you can use undetermined coefficients, which is the one where you take a guess. So based on the form, like if f of t is the sine function, you say, okay, a times sine plus b times cosine or something like that. Yeah, so either way works. But yeah, once you have this written down, now you just go back to chapter 4 or whatever, whatever chapter it was, and solve it using your normal methods. All right, what about the series circuits? So these are basically, it's the same. Like once you realize that there's no difference between, like, once you have the thing set up properly with the charges, the sum of all the, the charges is going to equal 0. So that's like voltage drops all add up, and the current all has to add up. And yeah, so this is the charge. The charge across each of the components in your circuit have to add up. That's basically what happens there. So was there anything with these? Like, did you have any trouble setting them up, or did you have any trouble solving any of them? I think didn't at least one of them had. It wasn't just. I think the first one was there was no electromotive force, but then the last ones had some sort of a battery or whatever. But anyway, do you have any trouble with any of those? Wow, it was easy stuff. Oh, that's so exciting. All right, or maybe I just did a good job 5 years ago. Or if you watch the videos, I don't even know what was going on, but yeah, it's the beginning. Yeah, I remember hearing on the radio a couple weeks ago, this is the beginning, like the 5-year anniversary of the beginning of the lockdowns. I was like, oh yeah, that wasn't very fun. But anyway, so let's go ahead then, and I got a text. Here, let's see. I don't want to show you any text I'm not supposed to show you. Oh well, I'll just read it to you. I got a text from Dr. Deborah Hewlett, which that's how I put her in my phone when she got her doctorate. I changed her to Dr. Deborah. She says, and I quote, wait just a minute. I put the differential quizzes from the printer in your mailbox. I answered with a thumbs up. So I left them on the printer, And so this is all I got for you. So some of you were excited about that. This is what's sitting in my mailbox, apparently, is this situation. And basically, I want you to, this is a non-driven, so this is just a spring mass system. And so I'll show you the whole thing in just a minute, but you can write down the important stuff up at the top there, and then I'll slide down and show you the initial condition. So basically it's just a little bit more practice, similar to what we're going to have on our exam. Oh, we have to talk about that as well. So if you were in my, I guess Joshua knows that there may be a change, but this is an optional change in this class. I will bend to your will. But we'll talk about it, yeah, because I don't feel as strongly about your class as I don't feel as strongly about your lack of ability as I do with my other class. How about that? Does that feel better? Okay. Yeah, I'm happy to do whatever you want to do, but we'll talk about that in a minute. Let us do this quiz first. So zoom this out a bit. Yeah, this is too small. Let me, I will put the initial conditions up top so that we can all see them, and then I'll zoom back in. So here we go. Okay, there, that's better. So basically you're solving this system and you're going to predict like what's going to happen. And then I guess you'll grade your own paper and you can just let me know if you got 100 or not. And I'll dutifully give you the grade that you tell me to give you. Oh, damping coefficient. I have C there, but it's beta for our book, right? I think I probably pulled this from my files. Just call that beta. I love how I have the units even. Newtons per meter per second. Okay, I'll give you another, I don't know, 30 seconds or so. We don't want to spend all day on this, but try to finish things up, and then we'll go over the answers together, see how we did. We're waiting for you. That's all right. All right, now we can go ahead and go over what we've got. Hopefully you've got the same thing as me, because if you don't, that means one of us is wrong. So we'll find out. So here's the differential equation once I find my clicker. Where did it go? Oh, there it is. It's hidden. There we go. So let's see, the mass is 1 kilogram, so that's 1 times x double prime. 6 is the, wherever it is, damping coefficient, so 6 times x prime. And then 13 times x is, 13 is the spring constant. So hopefully you have that as your differential equation. Very nice. Then we're going to solve this. I didn't bother going into the next block, but you didn't even have the paper, so you did this sort of thing. So that's supposed to be a 6, not an or. So that's the 6 there. So I did this thing with the r here, and then I was like, oh, it doesn't factor, drat. But I'm not going to give up because I know that I can use the quadratic formula. That looks fun. And, you know, maybe you got to this point and got excited like I did. I thought, oh, look, it's negative 16. That's a perfect square. And so this becomes negative 3 plus or minus 2i. Does that look right? Whew. You know, I never know. And sometimes when I'm collecting your quiz, I think, oh, I messed up. And then I can come fix it, like slow, try to do it on the sly. But anyway, so then because this is, the characteristic roots are negative 3 plus or minus 2i, the real part, that is going to go to the exponential piece, and the imaginary part, that's the sine and cosine. So just remember, it's like the imaginary, that's the weird stuff, so that's the sine and cosine. The real part is the normal stuff, that's the e exponential. So here's what this ends up looking like. Here we go. So you have, yours might look a little different from mine. It's fine. It might be rearranged a little bit. But I've got C1 times e to the negative 3t times cosine of 2t plus e. So you could have factored out the e to the negative 3t. That's the only thing that would be different, or switched the sine and cosine. But you should have something like this for the general solution. And then we can take those initial conditions and plug them in. And in order to do so, I need to have the derivative. And my heart sunk when I realized I had to use the product rule. But it's not that hard, is it? So hopefully, well, hopefully it isn't. Let's see how badly I did. I'm going to double check, scan this real quick. So this, I'm going to get negative 3c1 e, so that's the derivative of this, leave this alone, and then I do the derivative of cosine, and I leave the e to the negative 3t alone. Derivative of cosine is negative sine, and then you got the 2 that comes out, and then for some reason I did the derivative of sine, which is cosine times 2, and leave the e, and then you do the derivative of the e to the negative 3t. Okay, I feel good about that. Now we have to plug in the two numbers. Plugging 0 into these is pretty easy if you remember that sine of 0 is 0, cosine of 0 is 1, and e to the 0 is 1. So essentially, when I plug 0 into all of this, I get C1, and that's it. The rest of it is 0. So C1 is what you get when you plug. And then the bottom is a little bit more complicated, but we'll get to that. So the top one is easy. It's just going to be 5 equals C1. Bottom one, let me double check this one because that's a little bit more complicated because x prime of 0 equals 0. So that's what the 0 is on the left. Let's double check this though. C1 is equal to 5, so that's going to be negative 15 times 1 times 1, so that's that. This is 2 times 5 times 1 times 0, so I just ignored this. This is 2 times C2 times 1 times 1, so there's the 2C2. And this is 3 times C2 times 1 times 0, so I ignored that. So I got this, which gave me C2 is 7.5, 15 halves. Does that look all right? No one likes it? No, someone likes it. At least someone does. So if one of you likes it, then it's probably right. Then the final thing is just to write it all in a nice, beautiful, whole answer. All right, so we're okay with this? Okay, so let's talk about an exam. So the deal is that if we do the exam on Friday this week, so you heard the options, and I'm happy to discuss this. I guess we could do it Monday. You know, I don't care when it is. It's just got to be at some point. But I thought that at least for Joshua, it'd be nice if it wasn't next Friday, right? Joshua has another class with me, and he's got to take another test on Friday.
But it's also stats.
Yeah, that's right. You could do that in your sleep. So I'm happy to do it next Friday. It gives me more time to get it ready. But if it's this week, what it means is there's no Laplace transforms on it. If it's next week, it'll have Laplace transforms on it. So you don't even know what a Laplace transform is. You're going to learn in a few minutes. We could wait till the end, I suppose, and discuss. But if you have if you have concerns, maybe I'll try to set aside at 3. So in half an hour we'll talk. Let's still do. Okay, so let's do some Laplace transforms, and then you can say, do we want to do this or do we not? Yeah, it's like a completely different way of looking at differential equations, by the way. So, so you might ask why? Why would we care about the Laplace transforms? Well, back in the 1600s, a guy by the name of John Napier discovered that if he used logarithms, a lot of arithmetic was a lot easier to deal with. And so he developed a table of logarithms that scientists would use to do hard calculations and to simplify those hard calculations. Slide rules are based on logarithms, and in particular, the A scale and the B scale on a slide rule are logarithmic scales, meaning that if you measure the distance from the start to whatever number you're at, you'll get the logarithm of that number. So distances are logarithms. So for example, the beginning of the A and the B scale is 1 because the distance from the edge to the 1 is 0. The log of 0 or 1 is 0. If you go over here to 2, whatever that distance is will be the logarithm of 2. And honestly, I don't know what the unit is, or it doesn't matter. All that matters is that it's scaled correctly. Doesn't matter what base the logarithm is. And the reason why this is important is because when you're doing arithmetic, so this is for arithmetic. If you're doing arithmetic with real numbers and you convert to logarithms, what that does for you, okay, there it is it takes multiplication and turns it into addition. So you take a multiplication problem and it just turns into an addition problem. So on a slide rule, if I want to multiply two numbers like 5 times 6, I know. You can do that in your head. But just to demo, I would line up the 1 from the B scale onto the 5 on the A scale. There it is. Okay, it's lined up good enough. And then I look across the B scale till I get to 6. And lo and behold, the number that is above it on the A scale is 30. So it's calibrated this way so that if you want to multiply two numbers, you just slide this and line up things. And this is the way scientists did math. I mean, back in the 50s and the 60s until you had hand calculators. I remember my dad having a hand calculator that was pitiful. And he had paid like hundreds of dollars for it because back then that's what it cost for a hand. It's like, and it was LED, like it glowed red instead of, no wait, LCD, sorry, LCD. It glowed this red glowing screen. It was really bizarre, but you know, he was happy to have it, I guess. But anyway, so you take multiplications, turn them into additions. Division, if I want to divide on a slide rule, it's just subtraction. It turns it into subtraction in logarithms. So you take you subtract, you kind of do the opposite of what I just did to multiply. If you want to do exponentiation in logarithms, it turns exponentiation into multiplication. So it essentially simplifies the calculations that you have to do. And this sped up scientific calculations considerably, so that Napier, with his logarithms, became quite famous back in the 16 and 1700s, because people could do calculations much quicker. And I'm confident that it helped the scientific revolution for us to be able to use logarithms. Of course, these weren't invented till maybe the 1800s, I think. I don't know, there may have been some rudimentary slide rules before then, but you had to calibrate them. So that's the thing, is this had to be, the measurements had to be as close to perfect as possible. So that's logarithms. So you might say, why am I showing you this? Well, you have a similar situation when you think of Laplace transforms. So essentially, a logarithm is a transformation. It takes real numbers and turns them into numbers that are a little different. So you have the real number world and then the logarithmic number world. And they're different, but the logarithmic numbers, these measurements on here, allow you to do things much more simply. So here's the deal with Laplace transforms. With Laplace transforms, you take differential equations and you transform them. So we have all of our differential equations over here, and when we do Laplace transforms, which I'll show you in a minute how to do this, you can take an ordinary differential equation and turn it into a Laplace transform, and then it simplifies calculations. Now, just as back here, you're going to have to go both directions to do this properly. You take your real numbers, turn them into logarithms, you do your whatever arithmetic you need to do, and then you have to turn it back into real numbers. This is the hard part, is going from ordinary differential equations to Laplace transforms, and then do your whatever it is, and then you're going to have to go back. So that's the key. So here are the things that you do. In ordinary differential equation land, you integrate. You do this quite frequently, don't you? Whether you do it without, you're doing some integration, aren't you? Well, integration turns into algebra. So basically it takes calculus and turns it into algebra. Sometimes difficult, just to warn you, but algebra. So you're taking things that are hard and making them easier, sort of. If you're solving for constants, that you just plug in the initial conditions in Laplace transform land. So you know how you have to solve for the constants and all the rigmarole? No. In Laplace transform land, you just plug in the initial conditions and you're done. There's almost no work for solving for constants. So that's another benefit. Finally, knowing lots of integration techniques, you really don't need to. You just have to look up most of the functions in a table. So there are benefits to Laplace transforms, and some of you are going to be like, why didn't we start with this? Some of you are going to hate this, but it's just, it's just another way of solving differential equations. So let's do the basics first of all. So the Laplace transform itself, now I should warn you about this, is I'm going to show you the Laplace transform, and it looks complicated, but as I mentioned, we're going to be looking up most of our functions in a table, because once you know the Laplace transform of a sine, there's no need to recompute it each time. You just be like, oh, you know what it is. In fact, I know my Laplace transforms for exponential functions, for sine, cosine. I can guess it, the secant. No. So there's some that I'm not as good with, but and polynomials are really easy, the Laplace transforms of those. Okay, so let's talk about the Laplace transform itself. So I know this looks super, I should have had this build a little differently. But this is the definition of a Laplace transform, the top here. That's what we want to do, is this right here. So let's focus on that for a minute, and we will come back to the rest of this. So let us do this. Let's go, here we go. We'll do it over here. So the Laplace transform of a function is equal to the integral from 0 to infinity of e to the negative s times t times f of t dt. Did I get that all perfect? I think so. Let me double check though and make sure it's just right. Yeah, that looks good. Okay, So that's the important bit. So like I said, once we do one of these, it's kind of like when you're doing derivatives back in calculus. Remember Calc 1, you would do the derivative and be like, oh, it's always this way. Here's the rule. So you did a limit definition of the derivative. That was the painful part. But then you realized, oh, all polynomials are easy. So it's a similar deal with this. So let us do a Laplace transform for a function just to show you how this works. And maybe we'll do two functions. So here's the Laplace transform for e, I don't know, e to the t, should we do? Let's just do simple, nice simple. Okay, so this Laplace transform for e to the t is the integral from 0 to infinity of e to the negative s times t times e to the t dt. So pause for a minute, make sure that that makes sense, that that's the way this is going to work. You know what, as long as we've got that up here, I just want to show you one more. We'll do both of them. These are the two that we'll do. So we'll also do the Laplace transform of t squared. We'll do that over here. And that will be the integral from 0 to infinity of e to the negative st times t squared dt. So we'll do both of these by hand. It's going to feel like the limit definition of a derivative is just pain. But once we do it once, we don't have to do it ever again. So here we'll do this one on the left. The left one is easier. Before you start pulling integration of parts out of your brain, let's combine those using some algebra, and then it'll be much easier. Okay, so this is going to be the integral from 0 to infinity of e to the t minus s times t. So rules of exponents hopefully isn't too much of a problem. 0 to infinity of e to the t times 1 minus s dt. The only problem with Laplace transforms that I have is the fact that you have a lot of s's, and the s's look a lot like 5s. So I try to avoid the number 5. You'll never do the Laplace transform of sine of 5t. There's too many things that look like s's. So we'll try to stick with this s, no 5. All right, now at this point, you got two options, and I'm happy to do either. So why don't I do it this way? I'll just tell you what I'd like to do, and then I'll give you the option of making me do it the long way. So what I'd like to do is just to recognize that this is just e to a linear function of t. And so when I integrate this, I'm just going to be doing the chain rule in reverse, right? So this is e to the t times a constant. I know there's an s there, but that's constant with respect to t. So e to the t times a constant, and I'm going to get this divided by the constant. Like if this was e to the 3t, the integral would be e to the 3t over 3. If it was e to the 6t, it would be e to the 6t over 6. So that's what I prefer to do. The other option is to write out the substitution. In particular, u is equal to t times 1 minus s. So I don't want you to feel like you have to do it in your head the way I'm about to, because you could do this and then work out, then you're going to have to do a little bit of rearranging. We need to put a 1 minus s in here, so we have to divide everything by 1 minus s. But either way you cut it, your final answer ends up looking like this. E to the t times 1 minus s all over 1 minus s. Evaluated, I'm going to do it correctly. Sorry, I know this is going to be annoying, but I'm going to do it the right way. B approaches infinity. I should probably label these. Let me do that. This is t and t. There. So seriously, if you need the substitution, you should use the substitution. So technically what I did was I did this, and then I did that. So that's, the substitution is where this 1 minus s magically appeared. Okay, let's see. I'm going to plug in, let's see, so the limit as b approaches infinity of e to the b times 1 minus s over 1 minus s minus e to the 0 over 1 minus s. Is that right? Did I do that correctly? All right, so let's pause for a minute, make sure that we're all on the same page. Is there any algebraic or calculus problems that we need to talk about? All right, let's do this limit. So I want the limit as b approaches infinity of this thing. All right, let's pick a volunteer. Hold on a sec. This is fun. Take it in, smash, random. Here we are, random. Max. Max gets to do it. Max, do you know what the limit as b approaches infinity of this is?
It's gonna be infinity.
It might be infinity, you're right. Any other options? So it could be infinity. I was hoping he'd say, I don't know, but you're too smart for that, right? So, Matthew, do you have any other options? Could it be anything other than infinity? Could be 0. Yeah, we don't know. Yeah, it could be 0, could be infinity. Here's the problem. That s there. You see the s? What if s were bigger than 1? Let's say s was, say, 2. Then Matthew's right. It's 0, because this would be e to the negative b, and the limit as b approaches infinity of e to the negative b is 0. But if s were less than 1, like if s was 0, then Max is correct. And this would be e to the b, and the limit as b approaches infinity of this is infinity. So here's the trick, is when we're doing Laplace transforms, what you want to do is think of b, or s, sorry, s. You've got this s that shows up way here at the beginning. So s, where's s? What is it? Where does it come from? What is it? So s is sufficiently large. We don't know what the value of s is. We don't care. It is a number, or it's not really a number. It's a function. We'll get to it. Give me a minute to get the answer, and then we'll talk about s. But for now, just think of s. S is sufficiently large. You might say sufficiently large for what? Well, sufficiently large so that Max can't tell me that the limit doesn't exist. Because I want the limit to exist. So if there's an issue with the value, with the size of s, just be like, s, it's bigger than that. So even though Max was correct in his evaluation of this limit, as long as we assume that s, so maybe if it bothers you, I could say let s be bigger than 1. So as long as s is bigger than 1, we're good, right? Because this limit will be 0, and you'll get, so this will be, it'll be the way Matthew did it, it'll be 0 minus 1 over 1 minus s, which is equal to 1 over s minus 1. And that is the Laplace transform of e to the t. So anytime there's an issue, you just say, s is big. How big? Well, it's bigger than 1. Okay, now let's talk about at least one way to think of this. So back with your, whoops, get this back up here. Here we go. So back when we were dealing with real numbers and logarithms, you had real numbers which are measuring things in one way, and logarithms measure things in a different way. You can look at this. It looks like a ruler. It's marked off like a ruler, but the measurements are logarithmic distances, not actual ruler distances. The 7 and the 8 are much closer together than the 1 and the 2. So logarithmic differences, you have a sort of a different way of measuring. That's one way to think of logarithms and to make it make sense. Then when we get to this, differential equations, So here's the way I think it helps me, is that we're dealing with time, so t. So the variable, the important variable is time. So time is equal to t. Laplace transforms, the variable is no longer time, no longer t. You have the variable s. And I don't care how you think of the variable s, but one way I think of it is that I've gone through some wormhole and I no longer am in our normal time. It's like when the kids in the Pevensies, they go to Narnia and time changes. So this is Narnian time and this is our normal time. So however you want to think of it, this is a different way of measuring time. So just like this is a different way of measuring distance. Sort of a similar deal here. So S, so time or whatever it is, I don't know, we could call it time, or we could call it sime. No, that's dumb. Just time. Time is now S. S is the measurement for time. And so what that does for us is it changes the function. So since we've changed the way we measure time, now instead of saying that our function is e to the t, so here maybe I'll even make here we go. This is our normal functions, and this is the Laplace function. So this is our first table. E to the t is our normal function, 1 over s minus 1. That's in Narnia. That's what the function would look like. So different way of measuring time. Let's do one more, and then we'll talk about the exam, which I'm happy to compromise. Okay, so here let's do this Laplace transform. I know it looks like a nightmare, but it's not as bad as it looks. So let's find yet another volunteer. I guess you'll take a minute to write that down. You know what? I'm going to, well, no, let's just give it a go here. So after you've got it written down, think to yourself, what technique or method are you going to use? So think of a technique or a method that you might have learned in Calc 2 to do this sort of an integral. It has nothing to do with the infinity business. It's the product is the problem. So come up with a method that we want to use, and then we'll see if we can use it. All right, Rachel P., what method do you want me to use? I'm not going to make you do it. Just come up with a method. All right. Do you know any methods? Sure you do. I know you do. I'm putting you on the spot. Sorry about that, Rachel P. I'll pick a friend of yours. Don't worry. Austin knows, but he's interviewing. So Tyler, what do you want to use? What method do you want to use?
Integration by parts.
Integration by parts. Yeah. So you could have said like integration by substitution is another method. That doesn't really work here, but that's a good guess because when we see things like this, we might think, oh, maybe substitution works. You probably don't want to use integration by trig substitution. We don't want to deal with that. But yeah, so one of those methods, it's going to be integration by parts in this case. Let's use parts. And in fact, I'm going to use parts by tables. And so let me remind you how that works. Whenever I do parts using tables, I set up my u and my dv, and then I just work from there. So my u is going to be t squared. My dv is e to the negative s times t. And we're going to do derivatives of u. The derivative, I should have made someone do that, but too late now. Madison, what's the derivative of 2t? I did the derivative of t squared, but what's the derivative of 2t? And then what's the derivative of 2? Yeah, there you go. So if you're doing integration by parts using a table, you have to be able to take one of the functions and turn it into 0. Usually it's going to be a polynomial, and you drill down until it's nothing. Very nice. Now we have to do antiderivatives to match those derivatives. So we start with dv equals e to the negative st. All right, Adric, what do you think? Can you do this antiderivative? What's the antiderivative of e to the negative st?
Negative s.
So let's see. So you have negative e to the negative st, and you say there's an s here somewhere.
Yeah.
So I'll put it on the bottom maybe, because yeah. So you correctly noticed that the derivative If I was doing derivatives, you would multiply by s, but I'm doing antiderivatives, so you do the opposite, which is divide by s. Very nice. Let's see if we can do this one more time, see if you got this. Zechariah, what's the next so let's do another antiderivative. So it's just with respect to t. I know there's the s there, makes it scary.
E to the negative s to t over s squared.
Very nice. So it's just another instance of doing this antiderivative. So yeah, you get e to the negative st again, and then you divide by s times s, which is s squared. I'll do the last one just for fun. It'll be negative again, e to the negative s times t over s to the third. So on the left, whenever you're doing it this way, you do derivative. On the right, you're doing the antiderivative. But anyway, it's not really that important because once we get done with this, you won't need to do this ever again because you'll have it on your table, well, when we get to it. Okay, so now the next step is to draw diagonals like this. And bear in mind that you alternate from positive to positive as you go down the table. So my final antiderivative of this original function, which we'll put it back on the screen in a minute, is going to be t squared times negative e to the negative st over s. Let's see, minus, because of this negative here, 2t times e to the negative st over s squared, and then minus, because of this negative, e to the, let's see, 2e to the negative st over s cubed. I believe I got all those right. Yeah, sorry, there's so many negatives, so much negativity in this table, it's terrible. But I believe I got all there's the negative there. This one is negative because of this, and then this is plus a negative, so that's negative. So whatever, however you cut it, now we have to do our limit, don't we? That's the worst part. So we're going to do the, so this is going to equal this stuff evaluated. It's going to be a limit as b approaches infinity, and this is t goes from 0 to b. Okay, so when t equals 0, that's going to be the easy part. Here, give me a sec here. Limit as b approaches infinity of, here, maybe this will be helpful if I do it this way. B squared minus 2b, that'll be negative b squared, times negative 2b minus 2, all times e to the negative s times b. Oh, there's different amounts of s. Crud. Oh. Over s squared, s cubed. Okay. Sorry. I forgot about the s's. Okay, but okay, that's what I get when I plug b in, and then I subtract, but it's subtracting a bunch of negatives, so it's going to be plus. The only thing that doesn't go away because of zeros, those are both 0 because t equals 0. So the only one that doesn't go away is the last one. So that's going to be 2 times, I guess just 2, over s cubed. Okay, let's deal with this. I need to know the limit as b approaches infinity of that. You know what? It would be probably easier if I made it into a fraction like this. Let's do this over e to the s times b. Here we have the same issue that we did above or over there, and that is, what is s? S is sufficiently large. So think of s as being a big number like 10 or 100, however big it needs to be. So as b goes to infinity, which of these is going to dominate? Which one's bigger? So let's see, pick a volunteer. I know you know it. Asol, which one of these? What's the limit as b approaches infinity of this fraction? Do you want to guess? It is 0 because exponential functions are huge compared with polynomials. I know b squared, infinity squared is huge, but e to the infinity is even bigger. So you could also do L'Hopital's rule 3 times, and you would find that this is some constant over an exponential, which once again would give you 0. So that's going to be 0. That means that the whole thing is 2 over s cubed. Thank God that's the only time we have to do that. So this is t squared is 2 over s cubed. There it is. That's the Laplace function. The first two Laplaces. So in general, though, thankfully, we're not going to do this a bunch of times because in your book you'll find this table, and I will have a addenda to this table where someone's already done these. Notice that here, let's take a look at this letter B. Letter B here, it says the Laplace transform of t to the n is n factorial over s to the n plus 1. So that means that the Laplace transform of t squared is going to be 2 factorial over s to the 2 plus 1, which is 2 over s cubed. Hey, that is exactly what we just computed with that long, terrible calculation. And here it's done for us. What about the exponential? Look at this exponential. The Laplace transform, let's do e to the 7t, just to be a little bit different, is going to be 1 over s minus 7. And you're done. So Laplace transforms will be using some tables and trusting that someone has gone to the trouble of actually computing these. Now that doesn't mean that you're not going to have to compute any integrals. There will be a few, but not many, so not to fret. So anyway, we'll have these tables eventually. So let's talk about the, oh yeah, you probably are embarrassed to talk about it. Okay, well let's do it this way. I don't mind doing the test on Friday. Is there, are there other things going on this week? Oh, there's a play going on this week. Yes. Andrew is just crushed. Never mind, I figured it out. So next week, the question is, I guess it's either Wednesday or Friday, and Josh says he doesn't care. So Friday's fine? Yeah, let's do Friday then. So yeah, we'll just push it to Friday. Yeah, sorry, play takes precedence. So we'll do it Friday. There will be some basic Laplace, nothing hard. It'll be basics, but we'll do this. I'll have to get the homework together. I wasn't sure how far we did today because I didn't know. You guys must have done a great job on Friday because I didn't know where you would be in terms of this stuff. So let me put this stuff together online for the homework before I leave for home, and we will have the test next Friday. That is different from the syllabus says this Friday.